So last time we had the introduction to gas turbines for power production. I like to think of it as hooking up right here on this shaft and making electricity, hooking it up to electric generator and for power production. We haven't moved into gas turbines for propulsion in the sense of thrust on aircraft. We'll get to that, but not today. So we had the basic Brayton cycle, and it had a compressor, it had a burner, it had a turbine, and it's basically the fuel is mixed in the burner, and then you have exhaust gases, and they're typically, well, they're expelled. I mean, there's these products. But here, what we did is for a cycle, we put it through a heat exchanger and closed the loop. All right. Now we want to look at enhancements to the performance of that. So we'll talk about regeneration. We've seen regeneration with the vapor power cycles, and it's the same exact concept of why we want to do that. We don't want our expensive fuel to be bringing heat into the working fluid at low temperatures. We would like that heat to be brought in at high temperatures. All right, that's the idea behind regeneration, both for the vapor power cycle as well as the gas power cycles. Reheat, same idea. Continue to bring in more heat, again at high temperatures, so maybe you expand through one turbine, then put it through a reheat, expand through a second set of turbines. And intercooling, though, is very different, very unique. But if anybody's had an internal combustion engine, maybe you had a supercharger, maybe you had an intercooler, or maybe your friend had an intercooler with that engine, and you're saying, what is that all about? Well, that's right here. It's the same idea behind the Brayton cycle enhancement. But there's nothing like an intercooler in the vapor power cycle. Okay, so let's jump into it. So what do we have after the compressor? Even though it's pretty warm, it's still cold compared to the high temperature that goes into the turbine. And if you burn your fuel in the combustor to take it from T2 up to T3, you're burning fuel to heat it up when it's relatively cold. So what you do is you say our exhaust products coming out at 4 are pretty hot. Actually, they're hotter than T2. If we look at a typical temperature entropy diagram, T4, the exhaust products, are higher temperatures than T2. Why don't we exploit that temperature difference so that we don't burn expensive fuel to heat it up for this low temperature range? We only burn the expensive fuel to heat it up in the high temperature range. So that's the basic idea. So what we'll do is we'll put basically a heat exchanger. It's a regenerator, they call it, or a heat exchanger. It's just a heat exchanger. And so there's no heat transfer with the surroundings. It's just between the two fluid streams. And so you can think that it may be possible to get the temperature of that stream coming out right before it gets to the combustor. That temperature is state X. This is just what the book does. I'm following the textbook. If I was the author of the textbook, I would not use a letter for a state. They have used numbers for states very consistently through all the textbook up to now, right? But now, guess what? There's state X and state Y. But you see X, first thing you think of is quality. And Y, you think, oh, some mass fraction splitting in the vapor power cycle going down to some feed water heaters. Well, sorry, we have to recycle variables. And so this is just another state, they state X. That's just what the book uses, so I'm going to be consistent with it. All right. So the temperature at X could be as high as the temperature at 4. Then you would have had a bunch of heat transferred over, and then the temperature of Y in that case would be all the way down to temperature at 2. Y is the exit temperature of the exhaust gases. So they come in with a Regenerator Effectiveness. Here is the effectiveness. I could have just as easily called it an efficiency, but let's not worry about that. Let's just stick with the terminology in the textbook. And it says, this would be the maximum change an enthalpy of either of those fluid streams. Think about the fluid stream that's coming in, going into the combustor. Okay, it could come out as high as H4. It came in at H2, so the change in the enthalpy maximum would be H4 minus H2. What did it actually achieve? Well, it'll be some percentage, some fraction. Hx will be less than H4. And so it may be 80%. This may be given to be 80% or 90% or 95%. It'll never be over 100%. And that's the regenerator effectiveness by definition. Now, they do it in terms of enthalpy, but a lot of times we use constant specific heats. If you use constant specific heats, I think it's a little easier to understand because you have the temperature show up. And what cancels? The specific heats. If you use constant specific heats. So maybe I need to caveat that. This is constant specific heats. All right. And then it really makes sense because we use the temperature entropy diagram. We haven't used an enthalpy entropy diagram to understand these cycles. So it really makes more sense to talk about the temperature. Okay, but there you go. So this is one way to use it again. All right. How would I normally get a very large effectiveness, a very high effectiveness for my regenerator? I would make a large heat exchanger. I mean, really large heat exchanger. Large surface areas so that I have minimal delta T's. And there you go. But that's a subject of another class, ME4313, heat transfer, which you may have already taken or may be in or will take soon. Okay? But the principle behind that is if I need to move this much heat, the rate it's transferring, it's some convection coefficient, often that's low for gases, and some area, so you want some large area, and then some delta T. Well, we'd like this delta T to, be restrained. It's maximum delta T. Usually this is a log mean temperature difference, something like that in the heat exchanger. And if you want a large Q for the fixed H and delta T, it's pretty basic. Make area large. Big area. Okay. So we can solve a problem. Now what I'd like to do is solve this problem maybe in Excel. I know it'll take me more time in this lecture to do it, but I encourage you to solve some problems in tools to help you avoid making errors. And so instead of teaching IT, the software, or EASE, that's another software program that other people who've taught this class have used, I just use basic Excel. It does the trick. And it's very ubiquitous. And when students graduate, they come back and they share, oh, this is the new job that I have and this is what I'm doing. And I usually ask, what type of tools do you use? What software tools do you use? Do you use MATLAB? Unless they're in graduate school working on a thesis, it's usually no. Do you use IT? No. EASE? No. They may use some proprietary software if they're doing some detailed calculations, or they almost 95% say I use Excel, a lot of Excel. So there you go. We're going to use Excel. Let's understand this problem. Air enters the compressor of a regenerative air standard Brayton cycle. So this air standard, that's all information in there. Oh, we have this, it's ideal gases, it's only air, forget about the products of combustion. We're going to close the loop, make it a cycle. It's a regenerative. Hey, we have that regenerative heat exchanger in there to help improve efficiency. Okay. It gives you a volumetric flow rate of 75 meter cube per second at 1 bar and 290. That's what enters the compressor. So if you wanted to, you could say, well, I use the symbol AV subscript 1 for at state 1, the volumetric flow rate is 75 meter cube per second. And then we have P1 is 1 bar. I like to move that right away to kilopascal. That's my preference. You may have the preference of working in megapascal or staying in bars. That's fine. And then the T1 is 290 Kelvin. And because we often use the air tables and we use temperatures in absolute scale, it's nice that it's in Kelvin already. If it was degrees C, I would convert it to Kelvin. Okay. The pressure ratio. Now, I don't know if I've emphasized it yet, but in the textbook, what is R? It's the compression ratio used for the Otto and the diesel cycle internal combustion engines, right? All right. What is the single letter designating the pressure ratio in the textbook? Is there a single letter? Maybe RC. Oh, no, that was a cutoff ratio. How about RP? Maybe the pressure ratio? Not. No. Not. They could have. They could have introduced a single, letter with a subscript as, oh, this is my pressure ratio. But if you scour the textbook and say, what is their symbol for pressure ratio? It is nothing but P2 divided by P1. That's it, which is pretty obvious. It's a ratio of pressures, and it's the pressure at the exit of the compressor compared to the pressure at the inlet. So P2 divided by P1. It's 22 is the pressure ratio. And then the maximum temperature, and we know from our cycle analysis that's going to be the T coming out of the combustor or burner, and that's going to be T3, and that's a 1900 Kelvin. The isentropic efficiency of the compressor is 88%. If you've solved a few of these problems right there, you just breathe a big sigh and go, oh boy, this is going to be a long problem, is it not? Do you know what I'm talking about? Yeah, it's a long problem. I got basically multi-step state going around that compressor, because if isentropic efficiency of the compressor is 88%, all right, it's going to be a lot of work to do that. Oh, and the turbine isentropic efficiency is 93%. Oh, and the regenerator effectiveness is 80%. I anticipated the regenerator effectiveness, but these are 93% for the turbine isentropic efficiency is just a lot of work, as well as 88% for the compressor. All right, assume ideal gas behavior. Well, that's really embedded in the air standard analysis. This is repeated information. They could have left that out. All right, I mean, just like this. Assume steady state behavior. Yeah, there's no transient behavior in the problems that we solve. Assume, I don't know, something else. Neglect kinetic and potential energy. Does it say it in here? No, but it could have, but it's like we've not solved the problem yet. When we get to the exhaust on the gas turbine, where you want a high linear momentum flow rate out, you want a high speed V, that's when the kinetic energy at the exit's not negligible. Okay. Here are the constant specific heat values. So assume constant specific heat with K given, C sub P and C sub V for air given. Determine the net power developed in megawatts. So that would be something like W dot net. So many megawatts. Okay. The rate of heat addition in the combustor. That would be like Q dot in the burner or combustor in megawatts. And then the thermal efficiency of the cycle. Thermal efficiency, or just leave off the subscript TH. It's the cycle thermal efficiency. So many percent. That's part A, part B, and part C. So what's our standard template or recommended procedure to solve a long problem? After you read it and understand the information that's given, you want to generate a schematic. What are my components? What are the states between the components? Label those states. All right. Okay. That's basically, this is the schematic, and those are the states. I'm not going to change them. I'm going to stay with those states. All right. What else do you do? Probably get a property diagram to help you in your organization of information. And so this is what that property TS diagram looks like. So both of those have been done for this problem. That's right there. What's the next step? After you have your schematic with states, you have a property diagram. Get a table of properties and then get a table of energy transfers for each of the components. Okay, so if I get a table of properties, and how many states do I have? I have state 1, state 2, state X, state 3, state 4, state Y. All right, I ran out of room there. Sorry about that. And then what about my energy transfers? I'm going to have some energy transfer in the compressor, energy transfer in the combustor, energy transfer in the turbine. And this is where students will be thrown for a loop. Because as shown, is this a cycle where the fluid goes in a loop continuously? Or is something missing that prevents it from being a cycle? Conceptually, you have to add right over here, let me erase, a HX, where you bring this fluid down, so it's coming in at state Y, and then it's going out as state 1. Now I've closed the loop. Because what's really important is there's a heat transfer from this heat exchanger out to the surroundings. You say, well, why didn't they put that in the schematic? I don't know. Write a letter to the author of the textbook. I mean, but it's standard not to, for this textbook, to put that little heat exchanger in. But if you're going to do an energy analysis, you're going to have to reject some heat to the surroundings. Where else are you going to reject it? Not in the compressor, not in the combustor, not in the turbine, not in this regenerator, in this unshowed heat exchanger. So don't forget it. You got to close the loop. Okay. So you then have that energy transfers, Q's and W's for each component. Then you can do a table of metrics, part A, part B, part C, to compute these right in here. Let me do this before I move away from this slide. I probably am going to get the mass flow rate in the loop, so many kilograms per second. And if I could get that to calculate W.net, isn't that going to be the mass flow rate times the specific net work per unit mass going in the loop? Yeah, that's what that's going to be. And this W.net is the sum for the W column in my table of energy transfers. Hopefully that makes sense. I'm going to do that. But how do I get this mass flow rate? I'm going to use the volumetric flow rate right here. Oh boy, it's been a couple weeks since we've used that. So what's the relationship between the volumetric flow rate at state 1 and the mass flow rate, which is true? It goes through state 1, it goes through state 2, it's going through the loop. So it's not like we're losing mass anywhere or gaining mass. What do I do to get the relationship between the m dot and the AV? That's a question for you. Divide by or multiply by the specific volume at state 1. Will that work? Yeah, that'll work. You divide by the specific volume at state 1. How do I get the specific volume at state 1? It's always an ideal gas. Always, Professor? Always. For this, that's our air standard analysis assumption. So it's R T1 divided by P1 at state 1. All right, so I think we have a pretty good roadmap. So I want to leave now this slide. Hopefully you have good notes. And then I'm going to move just to Excel, and then I'm going to solve this problem in Excel. And I'm not going to try to jump back and forth. It'll be too confusing. Okay? So let's do that. And so what I like to do, that's just my style, is I like to put it in the first A1 cell, just a comment. And so I'm going to solve a regenerative air standard Brayton cycle. And I'm going to assume constant heats. Time permits, I'll go back and solve it with a different one. That's just a comment. I can take that cell right here and maybe increase its size and then make it bold, make it stand out, whatever you like. And I like to start populating information in cells in the upper corner. So I have the volumetric flow rate at state 1 given, and it's given to be 75. And then sometimes I'll put the units like this, meter cubed per second. Sometimes I'll put them over here. I'll put it like that, comma, meters cubed per second. It's just up to you. Sometimes you have to enlarge that cell if you put the units over there. Okay. And then R for my air. Sometimes I put additional subscripts on that. The units on the R are a little long, so I'm going to put them over here. It's a kilopascal times meter cubed divided by kilogram times Kelvin. Does that look like good units for my R, for my gas constant? And then I like to think of it as, okay, it's 8.314. That's R bar. And I divide by the molar mass of air, 28.97. I can remember that number to 4 significant digits. And there you go. Maybe I clean that up a little bit. I'll move over, boom, boom. And there's something more familiar, 0.2870. Good to, 4 significant digits. Make sense? Is this big enough to see? Can you see this okay? Okay, very good. So now I put in some more information. Maybe I put in, my pressure ratio, P2 divided by P1, and that was given for this problem to be 22, and there's no units on it. And then just to sort of tidy things up, I have CV given. I'm going to put the units there, kilojoules per kilogram Kelvin, and C sub V 0.718, and then CP, kilojoules per kilogram Kelvin. Hey, does CP and CV have exactly the same units? They sure do. And sometimes when you see that in engineering, you're a little confused, but things can have the same units and have different meanings. And then K is that ratio, 1.4 dimensionless. And then I know I'm going to use this one. I'm going to use K minus 1, and I'm going to divide it by K. I know I'm going to be using that isentropic relationship, so I'm just going to compute that K minus 1 over K once, put it in a cell, then when I need it, I will grab it. So that's equal to, in parentheses, K minus 1 divided by K. So it goes to cell G4, subtract 1, divided by G4, and there's K minus 1 over K. Now, I'll make a table of my different states. Maybe I'll put state here, state, and then I'll have 1. Then I'll go to the compressor. Now, if it would have just been the compressor, isentropic compression, no efficiency given, I would just say state 2. But now I got to do it in analysis steps. I'll have to go to 2S and then 2 actual because of that efficiency, isentropic efficiency. So then I'll go to state X after the regenerator. Then I'll go to state 3 after the burner or the combustor. Then I'll go to state 4S, isentropic expansion through the turbine. Then I'll go to 4 actual using the efficiency of the turbine. Then I'll go after, that'll go into the regenerator, and then after the regenerator is Y. And so I kind of know all of my states up front, and if you've not solved the problem before like this, then you basically have to figure those out. All right. So pressure, I need to know that in kilopascal. I like to work that. Temperature in Kelvin. And we're using constant specific heats. I can put V, the specific volume, in meter cubed per kilogram. And let's percolate and put in what was given. In our first state, inlet state, the pressure was 100 kilopascal and the temperature is 290. Is that true? All right. And then let's use our equation for the specific volume. It's equal to R. Come up to this cell, grab R for air, times the temperature there, divided by the pressure. That's fine. If you use Excel a lot, sometimes you like to drag cell the formula down. And so what I'm going to do is I'm going to move back here in my cursor back here to C3, and I'm going to hit the F4 on the keyboard And what it does is it puts the $C $8, meaning if I drag this formula around, don't drag it down or over for the formula. Always go back to that cell and always get that R. If you're not familiar with Excel, hopefully that makes sense if you are, but if not, that's what the dollar is doing. It's fixing it. Okay. So, whoops, what did I do? Did I hit escape? I have to do that again. Equal to this, then I'll hit the F4, then I'll hit multiply by the temperature and then divide by the pressure, and there's my specific volume. Okay, now we come over here and we say, let's finish out our pressure column. That's often the easiest thing to do. So, what is my pressure at 1 times my pressure ratio? And there you go. Let's say they changed the problem and they said, oh no, the pressure at state 1 is not 100, it's 90. Well, it just updated the calculation, didn't it? It updated this cell as well as that cell. That's the beauty of Excel. Can update values. Okay, so what about the pressure at this? Well, it's the same pressure, isn't it? Constant. I mean, state 2S and 2 actual. And then after the compressor, it goes through the regenerator, it's constant pressure. It goes through the combustor, constant pressure. But now it goes through the turbine, and state 4 is on the backside or outlet to the turbine. It's actually back down to state 1. And this is back down to state 1 pressure. And this is back down to state 1 pressure. Why do I do it that way again? Let's say I change it to 95. You see all of it percolated and changed? Yeah, that's, again, just showing the power of it. Let's go back to 100 for the inlet pressure. Okay, somebody says up here, what happens if it's 20 for the pressure ratio? It changes those pressures. All right, let's jump up here. 22 is the value we want to use. Okay, now, how do I calculate T2? Well, I'm probably on the side on a piece of paper. I remind myself of the equation, and I've done this a few times by hand to do that. And what it is it's equal to T1 times the pressure ratio, P2 over P1, raised to the power K minus 1 over K. Does that cell calculation make sense? And there you go. This has too many digits in here, so I'm just going to go ahead and try and clean them up right away. I'll put point something, 0.1 digit on it to help it look good for the whole column. I selected the whole column so I don't have to keep reformatting numbers. All right, now I have a choice. I can put it over here. I can put it a couple different places. It's up to you. Let's do this. The efficiency, the isentropic efficiency of the compressor in our problem was given to be 88%, right? All right. What I can do is I can say, well, what would be the work that the compressor needs if it was isentropic compression in units of kilojoules per kilogram? Well, wouldn't that be this specific heat constant pressure times this outlet temperature minus the inlet temperature enclosed? Now that's a positive work into the compressor. I know that I'm avoiding the negative sign. When I put it in the table, I'll put the negative signs in. All right. This efficiency, maybe I do it like that. Put it like that and put it over 88%. Okay. But now because I know it's 88%, isn't the work the compressor needs to actually intake is going to be greater, isn't it? In kilojoules per kilogram. So it's going to be the isentropic divided by the 88%. So I do it like this in my mind and when I solve problems. Does that make sense? So now I could come over here and I can say, okay, I actually now can say that's this inlet temperature plus that work actually going into the working fluid, but I have to divide by the specific heat because I'm interested in a change in temperature. And there you go. So if it would have been 100%, it would have come out at 701.4. but because efficiency is 88%, it comes out at 757.5. It comes out hotter. I look at it. I'm comfortable with it. I don't think I have an error. I can play with this. Maybe I put it at 98%. See, the temperature is much closer. Okay, how about this one? 99.99%. 100%. Change it back to 88%. Whoops, escape. Get it in the right cell. 88%. And there we are. At this point, I could grab that box, that lower right corner of my cell, and drag that down. And what it did was, it's going to work, I think. Come on now. It brings down the formula for the specific volume. Now, I'm going to grab all these columns. I'm going to just format them so it's easier to see them. Okay. So that's the specific volume at state 2A versus 2S versus 1. All right. Now, I have to bypass state X for a minute, and I'll come back to it. But they give me the temperature at state 3. Isn't that my maximum temperature in the cycle? Wasn't that 1900? Every now and then I like to color code stuff. Okay, if I color code this, maybe a light blue. And I color code this 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 a light blue. What am I doing is I'm basically color coding the pieces of information that are given to me in the problem statement. Okay. All right. Now at this point, I could grab this formula, copy it, move it down. I really don't need all these specific heats, but I can show them to you. Let's double check. Click this cell. It's going to take that pressure, that temperature, and that gas constant and calculate the specific volume at state 3. Don't need it, but it's nice to see it if I needed it. Okay. Now, how do I get T4S? Isn't that going to be the T3 times? Now here I can do 1 over the pressure ratio raised to the power K minus 1 over K. And it's much lower temperature. Okay. All right, then I come up here and I say, okay, but I'm going to have the efficiency of the turbine, which for this problem, the efficiency of the turbine's 0.93. So it's 93%. Let's convert that to make it percent. Okay. Then we're going to calculate the work that the turbine would produce if it was isentropic expansion through the turbine in kilojoules per kilogram. All right. That would be the inlet. Let's do C sub P first. It's C sub P times the inlet temperature minus that low exit temperature if it would have been isentropic expansion. 1120. But we have to calculate the actual work. And that actual work, oops, back up, okay, enter. That actual work is this isentropic work times the 93%. So we get less out. We don't get 1120 out, we get 1042 out, kilojoules per kilogram. So now we can actually calculate the exit temperature to be this minus this divided by the specific heat constant pressure because I want it back in temperature. So it comes out a little warmer. It comes out 863 versus 785. See that? You can play the same thing. Let's say it's 99.9% isentropic efficiency. Now those two match really well, don't they? So let's put it back at the 93% isentropic efficiency for our problem. Maybe I color code this and say, yeah, that was a given, that was a given into my problem statement. All right. Now I'm down here with 4, and here is state 2. So I go and I say, what is my regenerator effectiveness, REGEFF? That's just something, so it's not too long. Regenerator effectiveness for this problem was 80%. I'll make that, format it to percent. There you go. Now, at this point, I can think, what was my maximum temperature change? It would be T4 actual minus T to actual, I'll just kind of put that over here. I say, look at this minus this. So if I had regenerator effectiveness 100%, the temperature at X would be 863.6 and the temperature at Y would be 757.5, but we don't have that maximum change. This is the maximum temperature change. The actual temperature change would be something like Tx minus T2a. X is what comes out of the regenerator before it goes into the burner or combustor, and that's equal to this maximum times the, whoops, I messed that up. It's equal to this maximum temperature change times the regenerator effectiveness. And I need to clean up those digits. Right there, good enough. So this means that it's going to go up by 84.9 degrees Kelvin. So it's going to come out 84.9 degrees Kelvin higher, and this one's going to come out 84.9 degrees lower. Okay. I can drag this formula down if I wanted to. I can get all those specific, flow rates, and maybe that's important for another part of the design. Maybe I should color code this was an input. Again, if I start to change this, maybe I consider 99.99%. You see that the actual temperature change is the maximum temperature change possible, and this temperature at X comes out very close to the temperature at 4 actual, and the temperature at Y comes out right at the same as 2 actual. So you could play with the numbers in Excel to make sure. It's like, okay, yeah, that makes sense. All right, so now we go and we construct a table of transfers, energy transfers. I like to put in what are my components, and then I'll put in the components right here of a compressor. Oops, I hit the caps. Compressor, and then we're going to have, if you want, you can put in the regenerator, but the regenerator doesn't have any energy transfers with the surroundings, and so it's going to be a 0-0. But I think some students are going to be wanting to very tempted to think, oh, it has a work transfer with the surroundings or a heat transfer with the surroundings. It doesn't. It has a heat transfer internal to the cycle. So just leave it off. Just leave off the regenerator. You have the burner or combustor. You have the turbine. And the one hidden heat exchanger, typically not shown in our textbook, but needed to close it and make it a cycle. All right, we're interested in the Q's in kilojoule per kilogram and the work in kilojoules per kilogram. Maybe I don't like it. It's too close to that one, so I'll cut it, move it over, paste it. Maybe double click this so it just makes it a little bigger. Maybe put a box like this, come up here and format it, put a all borders box. Maybe I like the box style, put a all borders box there. Maybe I like to, make this bold, come up here and hit bold. Maybe I like these bold, bold. And maybe I know I'm going to do the net or the sum down here, and I'll do those in a minute. But maybe I'll come in here and put net. Okay, let's do this. So for my compressor, isn't it adiabatic? Burner, there's no work. How about for the turbine? Adiabatic expansion, and the heat exchanger, no work. So 4 of those entities are 0. That's nice. And then for the compressor, isn't it C sub P times the delta T? But I already calculated that, didn't I? I have it sitting right here. That's the compressor. At this point, I like to put the negative sign because I like to sum that column. And so this is a negative amount of work not coming out of the compressor. It's a negative out of the compressor, which is into the compressor. Okay. How about for the burner? That's going to be my specific heat times my change in the temperature. The burner has to take it from 842.4 all the way to 1900. So 1900 minus 842, close paren. And that's what it provides. I'm going to clean these up a little bit. That one's fine. Okay, let's take a look. How about for the turbine? You know what? We already did that. It's right here, isn't it? All right, how about for that heat exchanger? Well, it'll be the specific heat constant pressure times, in parentheses, it has to dump from here back to there, okay? And because it's a heat transfer not into the working fluid but out, it'll be T1 minus Ty. And then that'll give me negative. And then when I want, I do the sum of everything in this column. And then I'll just drag that over. It does the sum in that column. And notice they are the same escape. 571.8 in both. So double thumbs up. I'm pretty confident that those numbers look good. QNet must equal worknet, and it does. Okay. Then I maybe calculate my m dot in kilograms per second. All right, so that's going to be my volumetric flow rate divided by my specific heat, not specific heat, specific volume at state 1. And there's my mass flow rate, that many kilograms per second. I'll leave all those digits, it's just needed. All right. So the first part of the question says, what was W net in megawatts? Well, wouldn't it be the specific work per unit kilogram per unit mass going through the loop times the kilograms per second? And because they don't want it in kilowatts, they want it in megawatts, divide by 1,000, and there's the answer. And we'll do this. Let's just clean it up. I'll leave it to 4 significant digits. There's the power out of the cycle, 51.5 megawatts. All right, that's the answer to part A. Sometimes I like to label things like that. Q in the combustor in units of megawatt. So how much heat released due to the fuel being burned in the combustor is there? That's our heat transfer. It's going to be our m dot times for our combustor or burner. That right there, and we want it in megawatts. And so there you go. So to get 51.5 megawatts of power out of the cycle, I have to supply 95.78 megawatts of thermal energy in the combustor. Then you can calculate the thermal efficiency of the cycle. It's dimensionless, and isn't it the ratio of those two? And so it's like, this is what I get out over what I provide, and I want to put that as a percentage, and if I want it to more digits, there you go, 53.8% thermal efficiency, and I think that was asked for in part C. And then I put, maybe since that's a little table, put it over here, and I don't know, you could color code it a little different. How many people have probably used all the little tricks that I've used right here in Excel? And you probably can show me more. Did I tell you I learn a lot from students? They'll come to my office and say, what you did was pretty clumsy. Let me show you something. They've shown me and taught me all kinds of stuff, especially when I was struggling with the dollars. Like, oh man, there's somebody like, come on, here, let me help you. There's this F4 key. Let's learn what that does. And then, bingo, so much more efficient. The same thing with formatting cells and cleaning it up, making it tidy. Well, there you go. How's that problem look? Let's just save this. Where do I want to save it? So, enough. Okay. Guess what we do for the next problem? So we come back here to our problem statement and we say Same numbers, different Excel file that I did differently, but it's the same values. And you resolve the problem. It's still a regenerative air standard Brayton cycle, but what are they asking you to do down here? Variable specific heats. Okay, you need to go and use the table for air properties accounting for temperature dependent specific heats. That would be table A22 in our textbook. On the previous problem with constant specific heats, did I ever use table A22? Okay, here's a little hint. If you're given a problem and it says something like here's K, C sub P, C sub V, don't ever go into table A22 because you're starting to mix and match, right? You're starting to go to table A22 to account for variable specific heats when the problem told you don't. Use constant specific heats. Stay out of table A22, right? Use equations like the P2 over P1 to the K minus 1 over K assumes constant specific heats for the T2 over T1, okay? Isentropic. Now, they come in and they say, no, use variables. Should you ever use T2 over T1 is equal to P2 over P1 to the K minus 1 over K? Should you ever use that equation now for this problem? No. A big no. Big, big, big. No. Because that equation assumes constant specific heats. Should you ever use this C sub P delta T for, no. Use table A22. Okay? So let's do this. Same problem. Let's now solve it using variable specific heats. It'll take me a little bit of time. Let's go back to Excel and do it in Excel. All right, so we jump back to our Excel sheet. I'm going to rename this sheet right here, rename it. I'm going to say constant, something like that. And then I'm going to add a sheet, click right there, and then I'm going to rename that sheet. What do you think I'm going to rename it? VAR, variable, right? Now, I don't like retyping a whole lot. So I'll go back to the constant, and I'll do a Control A. What did that just do? Grid it all, copy it all, select it all. Now I'll do a Control C. I just copied it. There's slicker ways of doing this, but this works pretty efficient. I come over here, I place my cursor in cell A1, Control V for paste, and now I can start at that point. All right? Okay. So I know that some of the information is going to get blown away, and I have to be careful because when I start blowing things away, like all of this information, I'm not going to use. I could actually just delete. When I delete it, it's, oh, you're dividing by 0 and a lot of stuff is messed up. Okay? Let me do this. Let me just say I'm going to put no fill, kind of clean that up. And then what I'm going to do is I'm going to put in an extra column right there. So I'm going to do an insert a column, and that column is going to be my PR column. What do you mean PR column? In table A22, do we not have VR and PR? But because the pressure ratios are given for the Brayton cycle, we're going to use the PR column. In the Otto and Diesel, our volume ratios were given. We used the VR column for isentropic conditions. All right, the other thing I need to put in is I'm going to put in another insert, is I'm going to have my H's. Those enthalpies have to come out of table A22. So I'm going to have my H's in kilojoules per kilogram. Hey, what was the units on this PR? They didn't give any. Don't worry about it. It's dimensionless. It's to do the isentropic calculations. All right. Now, it copied over my color coding, and I don't like that, so I'm going to just clean up that, and boom, there you go. So what you do is you say, I have to go into my table A22 and find P sub R at this temperature. Who has a table A22, and can they find my P sub R at 290? What do you get?
1.2311.
1.2311. Now, if it's in a table in the appendix, do you think somebody can get it into an Excel sheet, like an Excel add-in? Of course, a little bit of work. So you would say, let's call a function. Somebody did this. You're looking at them with the help of a student, actually. A really good student helped me do this. I should give more credit to the student. But it's so many years ago. And you just say PR_T. What's that doing? You can see what they're doing. They're suggesting, are you trying to get to these functions that are built in and have some add-in? And so it's PR_T for air. And when I see it, I just hit tab, and so now it's ready. So I want PR. I'm going to feed it T for the air tables. So I feed it this cell right there. Cell E8 has my temperature in Kelvin. Close a parenthesis. If you're interested, you could come up a lot of times and hit on this little, what is this key right here? It's like a help on your function help. And it says, oh, isentropic pressure as a function of the temperature in Kelvin. So this temperature has to be in Kelvin, and it's going to come back with the value 1.2311. Is that close enough to what our table gives? What did our table value? You had it. 4.2. Okay. There you go. Now let's kick over and give it some more. Here, let's do this. Something like that. Okay. Guess what? H is a function of temperature for the air table. That's it. I mean, there's a lot of stuff built in. And then we'll just go get that temperature, close paren. Look good? All right. Now you think, we're going to go to state 2s. Basically, you're using the equation that PR subscript 2, the PR at the new pressure, is equal to PR1 times that ratio of pressures. It's equal to this first PR state 1 times the pressure ratio. There it is. Now, it's like, so for this state, I like to label stuff right here, is knowing the temperature, I was able to get PR and H. Now, knowing PR at that state, I can get the temperature. How can I get the temperature? Go and say, give me the temperature as a function of PR for air. There it is, same table. You're going to do the same exact steps. And so here you go and grab that cell. Now, Excel's a little tricky. Sometimes you have to click outside or near a cell and then drag and sweep it underneath. I'm still struggling with that. Does anybody know how to help me on that? You know what I'm struggling with? It's sometimes I'm trying to complete a formula in this cell and try to select the cell as an input to that formula in the adjacent cell. And it's cumbersome. All right, nobody wants to volunteer to help me on that one, so I'll continue to struggle. And then this is the enthalpy as a function of PR for air, and there you go. So I have my enthalpies. Now, I come over here and I say I'm going to still use this efficiency, but this time I'm going to calculate the work that the compressor would consume if it was isentropic compression. I now have my H's, so I come over and I say, well, it's that H minus this H, isn't it? H2 minus H1. I don't need that parenthesis, do I? Delete that. Backspace, there we go. Right? And then, using this efficiency, isn't the actual work there? Yes, sir.
Whenever finding an entropy, sir, if you have to interpolate, does that still work as far as that formula goes?
Yeah.
Okay, thank you.
Yeah. It took a while for the student and I to work that all out because we're novices, but we built the add-in to do it.
That's amazing. Thank you.
How did you get the add-in?
I built it.
Yeah.
From scratch.
How do we get it?
Oh, how do you get it? I have to share it with you. I hesitate to do that because I want you on exams to be able to solve it by hand. I can share it with you, but you got to promise that if I give an exam problem, you still can do it.
I promise.
That was easy to get that promise out. Pinky promise, huh? Is that what you just said? Okay, come up here. Okay, I'll have to figure out how to do that. I'll post it out on Blackboard. It's add-in. If you have a Mac, I'm sorry. Every semester, somebody, oh, I got a Mac and I want to work this work and I'm going to work really hard to make this work. And every time, it's after many hours of the student's frustration, they just say it won't work. Sorry. Something about Excel doesn't have the features of the add-ins in the Mac environment that they do in the Windows.
Can they try OpenOffice, like logged in online? You can get it with your student ID.
Are you going to try that? And if it's successful, you'll help me write up a little how to do and post it in Blackboard Learn for other students. That would be really helpful. Really, really helpful. Okay? So, hey, something new.
I don't have a Mac to test it on that.
There's an Apple. She does back there, or he does. So, okay, well, let's press forward now because this is the actual work. So guess what? At state 2 actual, it's really the enthalpy we calculate. So this is a little tricky, isn't it? And it was first temperature, kind of state 1, then state 2s was PRs, and now H is what's used to calculate 2 actuals. So we come over here and we say, well, what is that actual enthalpy? It's this inlet enthalpy plus the actual added work per unit mass. And so that's our inlet, our actual exit enthalpy. If you wanted to, you could calculate that actual PR. It's not needed. It would be confusing. Let's avoid it. You don't need it. But we would like to calculate the temperature. So it's equal to the temperature as a function of enthalpy for my air. Again, you go into the table, and now it's like, okay, I know the H's. Now I want to interpolate to get the T's. All right, and then to close a parenthesis and done. All right. Okay, state X we have to avoid for a minute. We have to kind of go down here. Now, one of the things you could do with this is you can just do a copy there, and you can just do a paste of those cells, and it takes the formula. This basically is the formula P sub R T, and it says I'm going to take the cell to the right of this formula and use that for my temperature, which is exactly what we wanted. Has too many digits over there, sorry about that, but let's leave them. And this is my H as a function of T. Okay. Then, so this is like going at T, then we go P sub R. You know what? That's very similar to what this cell did, these 3 cells did. So I'm just going to copy them. Once you get good at Excel, it's... The only thing is this was my, this is the cell that was grabbing my pressure ratio. But I wasn't doing more adding of pressure, building higher the pressure. I was reducing the pressure as I went through. So I need to divide by that pressure ratio. And so there you go. So there is the new state 4S, the temperature, the P sub R, and the enthalpy. It's P sub R is what drives it. Okay. And then I come over here and I say, well, okay, now I know what my work or the turbine is. If it's isentropic, it'll be this enthalpy minus that enthalpy. Whoops, there. And then because of the efficiency, I only get 93% of that out. So I can come over here and I can say, okay, this minus the actual work out. So I don't come all the way down to 932.7 kilojoules per kilogram, but I only get down to 1016.3. So this is like now the H. And if you wanted to, you could just copy that cell because that's the same formula to calculate the temperature. How come that didn't copy? Copy, move that down, paste. All right. Now, the regenerator effectiveness is here, but instead of doing the temperatures, because we're variable specific heats, it's the enthalpies, isn't it? All right, so I have to eliminate or change up this equation. I can just grab that cell, move it over to the enthalpy, grab that cell, move it over to the enthalpy. Those are my changes in enthalpy. And then my actual enthalpy at state X minus the enthalpy at state 2 actual, it will be 80% of that delta H max. So this is still good. This is interpreted as change in enthalpy. So I come over here and I can calculate the enthalpy at state Y. That's going to be the enthalpy at state 4 actual minus this actual enthalpy change. And I can calculate the enthalpy at state X. It's going to be this enthalpy 757 added the 207. All right, at this point my temperatures are off. See, that's a bad formula, but I'm going to just drag this copy down because this cell used enthalpy as a temperature as a function of enthalpy. Likewise, this one's temperature as a function of enthalpy. And to clean up the temperatures down here, the same thing. So those all look good. If you want, you could do a control tilde. And a control tilde shows you all of your formulas in Excel. Control tilde. Now, it messes up your formatting because now when I do control tilde to go back, I'll have to shape the column widths to make it look reasonable. But there you go. Pardon?
I think, I don't know, if you undo it, it might, press Alt-Z, it might go back to the way it was. I don't know if it will or not.
Control Z?
No, Alt-Z.
Alt-Z? No, Control Z?
Oh, yeah.
Oops, that just went back.
Try that little arrow up there.
I'll hit escape, forget it. Control this. Okay, well, I think I just undid that formula. Okay, I'm going to drag this down, clean that up. Perfect. Okay, it looks like it looks pretty good there. So, walking around, let's take a look here. What about the works? That's still correct. That one's still correct. But the burner specific heat is my enthalpy at state 3 minus the enthalpy at X coming into the burner. All right, and then that heat exchanger, and I want that to be a negative, so it's going to be the H1 minus the HY. And these two need to match. If not, I mention that again and again, but the reason I mention that is because even when I do it, guess what? I need to check my work every now and then because sometimes I'll mess up. So I use it a lot. Okay. Then we have our net power. Notice that the specific volume calculation did not change, did it? Our specific volumes are the same. And so our mass flow rate is the same equation. And then our power is good. Now it changed. It was 51.5 and now it's 58.1. It changed a little bit numerically for the variable specific heats. And then the same for the what goes into combustor. And then the thermal efficiency, instead of being 53.8, is 55.4. And there you're done. That was a lot to show. A lot like this. I should move that over, clean it up a little. Move this over. Move that over. And there you go. I think that's it for that problem. I'll hit save. If you want, I guess I can post this file up there on Blackboard.
That'd be awesome.
All right? All right. Okay, let's press forward then. Now we can talk about having regenerative Brayton cycle. That's really good. Leave that regenerator in there. But we can add reheat. Why? Well, the concept is expand it, then reheat it in a second combustor, and then do it. You'll find this in practice. You'll have two sets of combustors in some elaborate power plants. Okay, probably no more than two sets of combustors. It just is too complex of engineering for the improvement in efficiency. On a temperature entropy diagram, what you're doing is you're getting up to that maximum temperature limit, metallurgical, seals, the problems with the materials in the engine, and then you'll expand isentropically. I'm just going to not do the two steps of isentropic and then the efficiency. And then at an intermediate pressure, you reheat it, It's at a lower pressure. Notice this line of pressure is your highest. You have an intermediate pressure and a low pressure now. At that intermediate pressure, you put it through another combustor, bring it back up to the maximum temperature, expand, and so you're bringing in more heat right in that reheat at high temperature. Good for cycle efficiency. Goes all the way back to Carnot. Same idea with the vapor power cycle. As much of your energy, heat transfer, bring it in at high temperature as possible. I don't solve a problem with that. The problems get more complex. Maybe next time I'll solve one with both reheat and intercooling. But first, let's talk about what is the intercooling. Well, this compression is very expensive. Compressing the gas, especially if you go to high pressure ratio. So what you can do is you can take it up to a certain pressure, stop the compression, put it into what they call a heat exchanger or intercooler. What's that going to do? It's going to reject some heat to the surrounding. Well, how is that going to improve performance? Well, because the rest of that compression is going to be less costly. It'll cost less mechanical work to continue that compression process versus if you would have just avoided the intercooling and just continued to compress. You can somewhat see that on a temperature entropy diagram, but really I'm going to emphasize that in the next slide. So what we do is we compress, we stop at that intermediate pressure, cool it. What's the lowest you could get it back down to? Probably back down to ambient, maybe T1 and TD. I know they have a letter there, more letters for states, but once you start with letters on states and you just stay there. It leaves T3 being the inlet to the first turbine. That's nice. And it leaves state 4 as the outlet of the last turbine, inlet to the regenerator. That's nice. I understand all that. Okay, great. Okay, so that's one reason they have the letters. Okay, so you leave it at the intermediate pressure, you cool it back down. The lowest it could get down to is this lower temperature T1, and then you compress again. All right, and the work of the compression, if you had this two-stage, is going to be less than, if you had two stages, less than the work compression with one stage. This two-stage with the intercooler will be less. And that's why you do it. All right. Well, if you really want to understand intercooling, you have to go back to this section, which is the very last section in Chapter 6, which was probably the most difficult chapter in all of the Thermo 1 course. And it had the longest title. Just look at the title. The title was Heat Transfer and Work in Internally Reversible Steady State Flow Processes. Wow. That's a long title. Difficult chapter, end of a long chapter, and a long title. And so anyway, here are some equations, 649, 651 version A, B, and C. Now, this equation isn't the key equation for us right now in the study, but it helps set the context. Okay, does this integral TDS look familiar? Yeah, right? And so when you plotted temperature entropy diagram and you had a process went from state 1 to state 2, and you had this solid line indicating the path of the process, something of the area under that curve on a TS diagram, visually, the area under the curve was equal to the Q, the rate of heat transfer per rate of mass transfer through that device. Integral TDS is equal to Q dot over M dot. That's assuming that this is a solid line, internally reversible expansion or process through that going from state 1 to state 2. Make sense? Little review there. Let's take a look at these versions of 651, because 651 is one of the most confusing equations in the whole class. And a lot of times people will say, no, I think that equation has an error in it. I think that's wrong. This version, the last version, neglects changes in kinetic and potential energy, So this is the full-blown version, so you neglect those two terms. And it has that constant specific is assumed. So if I'm trying to do an integral with the inside is the integrand's constant, can't I pull that outside the integral? And so this equation looks like VDP. Where did we use this equation? Through a pump. But what did we put into the pump? Liquid, saturated liquid. Are saturated liquids nearly incompressible? Yeah, that's why specific volume is constant. That's why it was up. But guess what? We're now doing not pumps, we're doing compressors. All right, do compressors take in liquids which are incompressible or take in gases which are compressible? They take in gases which are compressible. So now it's a little more tricky. But the same equation applies. We have this integral VDP. I see I'm out of time, aren't I? I'm going to have to pick this up next time. Can you promise me to go look in this chapter 613? Yeah, that section. Just review these equations. That tells the story of why we want intercooling. And it'll reduce the work per unit mass for the same increase in pressure. Thank you for your attention. I'll pick up there next time.